Hello. In this video, we'll review how to set up and solve a system of linear and nonlinear inequalities. Let's get started. So remember that to solve a system of inequalities, we want to begin by drawing a sketch of either our line or our curve, noticing whether it's a solid or a dotted function, and then shading correctly and finding vertices. So I've listed those as your 4 points, and let's look at an example of each of those 4 points with our first problem. So we have 3x plus 4y is greater than or equal to 12, and x minus y is greater than 4. So another way of saying this is you're trying to satisfy both constraints at the same time. So what x and y values would do that? So to begin, we could start off by recognizing what types of inequalities we have. So let's look at the first one. We have 3x plus 4y must be greater than or equal to 12. Well, that's a line because its degrees are 1 for each variable. So for line 1, we remind ourselves how we could graph that, either by finding x-intercepts and y-intercepts, or by getting y by itself. I prefer intercepts, so for example, to get the x-intercept, remember how to do that? That's right, we let y equal 0. So if you were to let y equal 0 here, you can cover up the y term and you would have 3x is equal to 12, so x must be, that's right, x must be 4. If 3x is 12, x is 4. So let's go to our graph and plot that point. 4, 0, 1, 2, 3, 4. There we go. And let's find our y-intercept while we're at it. And for y-intercepts, we just let x equal 0. So if we let x equal 0, plugging in 0 for x, we would have 4y equals 12, so that y is just 3. And we could plot that point as well. So we go up to 0, 3. There we are. Now, what kind of line is it? Is it solid or is it dotted? Meaning, do I include points on that line in my solution or not? Well, because of the symbol greater than or equal to, remember anytime we have the equal to, that is inclusion. So we are going to use a solid line. So carefully draw a line connecting those 2 points. I'll see if I can do that without making it curvy. It's okay. It's not the best. It's not the worst. Okay, so we have line 1. Now, as far as shading is concerned, we might be tempted to shade above the line because we see the greater than or equal to, but let's do a test point to guarantee that we're shading in the right spot. So remember, for a test point, you pick any point that is not already on your function. My favorite point, if it's possible, is 0, 0, because the arithmetic is a piece of cake. Let's take a look at plugging in 0, 0 into that inequality. You would have 0 plus 0, which is just 0, greater than or equal to 12, and then you ask yourself, is that true or false? Is 0 greater than 12? Yes, it is, which would mean we would want to include, sorry, I said yes when it's definitely false. No, it's not, which would mean we would not want to include 0, 0, meaning we need to shade where 0, 0 is not located. Well, 0, 0 is located below the line, so we will be shading above that line. So we're shading above our first line, and now let's move on to our second line. Let me switch colors for you. How about blue? Okay, so for our second line here, again, I know it's a line because the degree of each of those terms is 1. The highest power is 1. Well, we could easily get the x and y-intercepts there as well, couldn't we? What would our x-intercept and our y-intercept be? Maybe pause the video and try it yourself. All right, so for your x-intercept, you would have put in 0 for y, which would have meant we would have x equals 4. So when y is 0, x is 4. So we would have an x-intercept at 4, which is very interesting because that was an x-intercept for line 1, wasn't it? So right now we've already found a point where the 2 lines are intersecting, which is very, very nice. What about the y-intercept? Well, we could let x equal 0, which would mean negative y equals 4, or y equals negative 4. So when x is 0, y is negative 4. So let's plot that point down here. And then we can connect our dots with a solid line or a dotted line this time. That's right, it would be a dotted line because we did not have the equal to. So let's make our dotted line going through those 2 points and understand where to shade would be next. Where do we want to shade? Above the line or below the line? Well, we could pick a test point again. So we want to pick a point that's not on the line itself. 0, 0 definitely is a point that is not on the line. So let's check 0, 0. If you put 0, 0 into that inequality, you would have 0 minus 0 is greater than 4. In other words, 0 is greater than 4. Is that true or false? Well, 0 is not greater than 4. It's false, which means we do not shade where 0, 0 is present, which would be above the line. In other words, we are shading below the line. So if we are to shade above line 1 and below line 2, let me get another color here to show you where our solution region would be. Above line 1 and below line 2. So above line 1 and below line 2, wouldn't that be in this space over here? So that would be what we call our solution region that satisfies both constraints at the same time. In other words, any point that is in this space, in this shaded region, would satisfy both constraints at the same time. Notice it includes points on the first line, because that was an or equal to, but it does not include points on the second line, because that had the dashes. That meant that we did not include those points. They're merely boundaries, okay? So now we found our solution region. The last thing you'd want to do, this is just a quick review, is to find your vertices, which are the points of intersection that trap your shaded region. Well, this time, because it's just two lines coming together, there was only one point of intersection, and we accidentally stumbled into it, didn't we, at 4, 0. So this time, the only point of intersection was at 4, 0. But in general, to find the point of intersection, you would solve a system of equations, which is what we've been doing in this entire chapter, haven't we, in this series. So you could solve that system of equations by substitution, elimination, or by any of the matrix methods that we've studied, as long as it's a system of linear equations. So you would end up getting x equals 0 and x equals 4 and y equals 0 for the point 4, 0. So once you found that point of intersection, if it is in fact a point that also traps the shaded region, then you would call it one of your vertices. And in fact, it is a corner of our shaded region. So that is our one and only vertex in this case. But had there been a third constraint, like the line x equals 5, the vertical line x equals 5, it would have crossed the other two lines in two spaces, meaning we would have had two other points of intersections, which are in fact vertices. So we'd have to solve for those as well. All right, so this is this example. Feel free to take your time with it, try it on your own again. Maybe click on the Desmos link and play around with those graphs to see the difference, what happens when you change some numbers in your graph. All right, so we're going to apply these same skills now to nonlinear equations and inequalities. Let's continue. So in example 1, officially, it says, can you sketch the graph of the system of inequalities shown below? Be sure to label all vertices of your solution region. And the first constraint, if you will, the first inequality, is y is greater than or equal to x squared minus 5. So your first step, if you go back to your previous slide if you need to, was to identify what kind of graph that is and begin graphing it. So looking at the first one here, let's get a color here, maybe orange. What kind of graph is represented in y is greater than or equal to x squared minus 5? That's right, it's a parabola. So for that parabola, we need to remind ourselves how we graph parabolas, right? Well, this parabola's equation would have been y equals x squared minus 5, which would have meant that we had a parabola which originally had a vertex at the origin and another 2 points at negative 1, 1 and positive 1, 1. It's been shifted how? Up, down, left, right, do you remember? That's right, it's been shifted down 5 units. So if you took your original 3 points and moved them each down 5 units, at negative 1 instead of positive 1, we'd be at negative 4. 1, 2, 3, 4, point. Instead of 0, 0, when x is 0, we're now at negative 5. And instead of 1, 1, when x is 1, we're now at negative 4 for y. And then we can connect our points in a parabolic shape. So we know the trajectory is something like this. And it's nice and solid because we had the or equal to. Now, as far as the x-intercepts, do you notice that we're going to cross the x-axis twice? Yeah, so in fact, if you wanted to show off, you could find those x-intercepts by letting y equal 0. And if you did that, you would have x squared equals 5, eventually, once you move it over. And that would mean that x equals plus or minus the square root of 5, which is roughly something bigger than the square root of 4, right? So it's something bigger than 2 point something. Feel free to use your calculator to get a better feel for this. But for graphs, that's sufficient. 2 and change. So a little bit over here and a little bit over there. So let's fix our graph, make it a little bit better now that we know where we're going. And let's run into our x-intercepts correctly here. So something like that. and something like, oops, that was rough. Fix that one. Here we go, something like this. Okay, so not perfect, but you get the idea, I hope. Now for this parabola, we need to talk about shading. Am I going to shade above it or the points below it? And you might have an instinct that it's above because of the symbol greater than or equal to, and you would be correct, but let's verify that with a test point. Again, I pick a point which is not on the parabola itself. 0, 0, it qualifies. You can see that's my favorite. If you put 0, 0 into the first inequality, we would have 0 is greater than or equal to 0 squared, which is just 0, minus 5. So that's just negative 5. Well, is 0 greater than a negative number? Yes. So we would include 0, 0. Now, where is 0, 0? Is it above the parabola or is it below the parabola? That's right, it's above. So if we're including 0, 0, we better be shading above our parabola. So currently, to satisfy this constraint, we would be talking about any point up here that is above the parabola or on the parabola itself. Well, let's talk about our second constraint and see if you remember what we're looking at. We have x squared plus y squared is greater than or equal to 25. Do you remember what kind of graph that was from a couple chapters ago? That's right, it's a circle. If you don't remember, feel free to look back at our video when we were talking about the distance and the midpoint formula in the past. I think it was our very first chapter together. And when we're talking about circles, we're talking about circles of the form x minus h squared plus y minus k squared equals our radius squared. Okay. So this is our circle in standard form with the center of hk, so there's our center, and a radius of r. So in this situation, what kind of circle do we have? That's right, we have a circle whose center is 0, 0, the origin. So that's the point from which everything radiates. And what is that radius? Well, if r squared is 25, r must be 5. So we have a circle with center at the origin and radius of 5. Well, we can draw a sketch of that, can't we? From the 0, 0 point, I go up 5 units, so 1, 2, 3, 4, and 5. So I have a y-intercept at 0, 5. I could go left 5 units, 1, 2, 3, 4, 5. So I have an x-intercept at negative 5, 0. I could go down 5 units and I accidentally bump into my parabola, which is quite nice. I just stumbled into a point of intersection of the parabola and the circle at 0, negative 5. So I'll just write that down. I found a point of intersection by accident. And I could have also gone 5 to the right of the origin, 1, 2, 3, 4, 5. So there's a point. And notice that if I connect the dots here, I'll make it a little bit darker so you can see it on the white background there. If I connect those dots, we're going to end up getting our circle, but it will cross through that parabola again, won't it? Yeah, there it is. It's crossing once there in quadrant 2. It's also going to cross again. Oh, that's a rough circle. But it's going to cross again in quadrant 1, isn't it? In quadrant 3 and 4, though, it doesn't have, ooh, that's rough. It doesn't have a chance. Let me just fix that. That'll bother me. It doesn't have a chance to actually cross the parabola again, does it, in quadrant 3 or 4? Only in quadrants 1 and 2 is it crossing. So let me make another color here. How about red? So we notice that we are crossing in 2 places. So we have 2 other points of intersection that we're going to be on the lookout for before we call it a day with this problem. Okay, so we'll be looking for those points of intersection. But there's one more constraint that I need to put on my graph. Let me find a color that you might be able to see here. Maybe purple. We'll try. Okay, so what about this constraint? Can we see that? A little bit. Okay. The constraint here is one that bothers a lot of my students. We see just x is greater than or equal to 0. Remember, when you have x equals a number or y equals a number, those are lines, aren't they? In fact, this is a vertical line. It's saying your x value is always 0. Well, if your x value is always 0, isn't that the vertical line on the y-axis? And it's a solid line again. All of these were solid this time. So here is our solid line that we're talking about in our third constraint. So there's our solid line on the y-axis. And we're told that to satisfy this constraint, our x values are always greater than or equal to 0, meaning to the right. So we are shading to the right here. So we're shading to the right. Notice we haven't talked about where to shade for our circle, so let's go back up there and talk about that. Where would I be shading my circle? Inside or outside? Can you think about it? Well, it says greater than or equal to 25, so probably outside, but let's test a point. What point do you think I'm going to pick? Well, that's right. You know it's 0, 0. So if I put 0, 0 into my circle equation, I would get 0 squared, which is 0, plus 0 squared, which is 0. So that's just 0. Is it greater than or equal to 25? Is 0 greater than 25? No. So that would mean I do not include 0, 0, which is inside of the circle. So I must be shading outside, beyond the circle. So if I'm shading outside the circle, let's put all that together. If you're doing your homework in technology like my math lab or other softwares, typically you would use like a paint bucket to pick your correct region at this point. But let me use some colors here. How about we'll do black? Why not? Okay, so here we have to satisfy all three shading constraints together. We need to be, let's take a look for the parabola. Where were we again? For the parabola, we said we were shading above it. So above the parabola, so that was area in here. At the same time, outside the circle, so that would now be up here. And at the same time, to the right of the vertical line on the y-axis. So wouldn't that mean we're in this space? So that would be our shaded region, wouldn't it? Now, as far as finishing it off, we need to find those points of intersection that we missed, and then we need to talk about vertices. So how do we find points of intersection again? Well, that's right. We need to make a system of equations. So what points of intersection are we after? Well, I can see clearly one of them by accident. I can see where the circle hits the line, can't I? Yeah, the circle is hitting the line in a couple of spots. It's hitting the line at the point 0, 5, and it's also hitting the line at 0, -5, which I don't need to write again, but we can see it's hitting it there. Okay, so that's a point of intersection. But what about the two places where the parabola and the circle came together? What do? Well, let's take our parabola equation, which would have been y equals x squared minus 5. And let's take our circle equation, which was x squared plus y squared equals 25. And let's see if we could solve that system. Now, this is not a system of linear equations, but of nonlinear, degree 2 or higher. So in this situation, we could do elimination, but we'd have to be really careful, right? Only x squareds and x squared terms could cancel, not an x with an x squared or a y with a y squared. But substitution is kind of begging to be done here, but be careful. A lot of students will want to substitute for y because they already see y isolated. But notice what would happen if you did that right now. For example, if you were to take x squared minus 5 as y and insert that into y in the second equation, wouldn't you have to square it? That's right. And what kind of degree would you end up with? X squared times x squared. That's x to the 4th power. Now that's possible to solve, but we don't really want to do that unless we have to. That goes back to finding the zeros of a polynomial from many, many chapters ago. Instead, what would be easier, so let me erase that idea. We'll put that idea back to where it came from. Instead, wouldn't it be nice if we could isolate for x squared? So for example, in the first equation, I could rewrite that equation as x squared by itself equals what? That's right, y plus 5. So now I can take y plus 5 and replace x squared with it. When I do that, y plus 5 plus y squared equals 25. Now that's a quadratic equation degree 2, which you can solve by factoring or by using completing the square or the quadratic formula. In this case, when you do solve, you should end up getting two y values. And you can try any of those methods that we've studied in the past. But the two y values that you should be getting are the y value of, let's see, 4. Yes, the y value of 4 and the y value of -5. So you should end up with y equals 4 or y equals -5. Now what's interesting about that, when you solve that using the quadratic formula or factoring is easier, by the way, you'll notice here that we already knew what happened when y was -5. Take a look at your graph. At -5, the circle, the parabola, and the line all intersected. Okay, so we already found that at 0, -5. But to check what that would have been, you could have gone back to the parabola because it has the smaller degree and plugged in your y. If you plugged in -5, for example, you would have that -5 equals x squared minus 5, which would have meant that x squared equals 0 or x equals plus or minus 0, which is just 0, which is what we knew already. So that was this point here, 0, -5. But on the other hand, what if we replaced y with 4? So if we replaced y with 4 instead, we would have 4 equals x squared minus 5 when we plug them into the parabola equation. And what does that mean? Well, putting 5 on the other side by addition, x squared would be 9, so x would be positive or negative 3. So we'd get positive 3 and we'd get negative 3 whenever the y value is positive 4. Well, that's very telling because we were wondering what those two locations were. Now we know when x is 3, y is 4, and when x is negative 3, y is 4. Okay, so we've now found the 2 points of intersection for the parabola and the circle that were in quadrants 1 and 2. Well, that's nice because we can now finish our final answer. The question was asking us, could you find the shaded solution region, which we did, as well as any vertices? The answer is, of course. Here is what we found for our vertices. The vertices are those points of intersection which trap your shaded region, which in this case would be this point, which was 0, 5, as well as this point, which was 3, 4. If you're wondering about all of those other points of intersection, they would not be vertices because they're not trapping, they're not corners on your shaded region. So only the points of intersection which are actually trapping your shaded region are called vertices. Okay, now that was a lot. A lot of you probably are wondering what in the world just happened. So feel free to pause, go back, and watch this video as many times as you can until you can do a problem like this on your own. All right, so we've done a circle and we've done a parabola. There's one more I'd like to practice with you. Let's take a look. What do we have here? And see if you can do it yourself, of course. You're always welcome to pause. Example 2 says, can you sketch this graph of system of inequalities? And label, of course, all vertices. So what do we have? Well, we see here y is greater than or equal to x squared plus 5x minus 6. What type of graph will that be? Degree 2. What does that mean? Parabola. Good job. So we have a parabola. Now this one kind of bothers students because it's in what we call general form. It's in the ax squared plus bx plus c form. It's not the standard form with the vertex just looking at you, hk. So instead, what we could do is we could try to find the x-intercepts. We already know how it opens, right? It opens up. That's right, because of our positive leading coefficient. So we could say, okay, well, could I write this in factored form? Go ahead and see if you can factor this if you haven't already done so. Okay, what did you get? All right, yep, you should be getting x plus, what, 6 and x minus 1, because when you multiply 6 and negative 1, you get your negative 6, and 6x minus 1x is positive 5x. So that would mean then that we have x-intercepts where? That's right, we have an x-intercept at negative 6 and an x-intercept at positive 1. So let's go to our graph and draw our parabola. It'll be solid. So let's take a look. Negative 6 is 1, 2, 3, 4, 5, 6 right there. And positive 1 would be around there. Okay, so we have our two x-intercepts. We could also, if we really wanted to do a nice graph, we could get the y-intercept by doing what? That's right, we let x equal 0. You could go back to the general form, it's easier. If x is 0, what do you have left? Yeah, negative 6. Or you could have done it by plugging it into the factored form. Either way. So negative 6, 1, 2, 3, 4, 5, 6 is down here. And now I could draw my basic parabola opening up, and it's solid. So something like this. If you want to find the exact location of the vertex, feel free to use your vertex formula. But for a basic sketch, this will do the trick. We have a basic sketch with our intercepts. So now let's talk shading. Am I shading above the parabola or below the parabola? Again, you could use a test point, or you could just simply look at the inequality symbol. Because it's greater than or equal to, most students will know it's going to be above. But let's pick a point like 0, 0 again and test. Well, 0, 0, if you plugged it in to the original, you would have 0 is greater than or equal to, that's right, negative 6. Well, is 0 greater than negative numbers? It is. So we would include 0, 0, which is above that parabola. It's above the parabola. So including it, we are shading above our parabola. So currently that's where we are, somewhere in this vicinity. Okay? But let's look at our second graph. What do we have here? We have y is less than 2x plus 4. Now what kind of constraint am I looking at here? What kind of constraint is that? That's right, it's a line. Well, we're great at lines. Y equals 2x plus 4. I hope we're great at lines. We might need to improve on lines if we're not great at them. Okay, so for a line like that, you could get the intercepts right away, or you could just recognize it's already in slope-intercept form. So I know that the y-intercept is a 4, so 1, 2, 3, and 4. And the slope is 2, so up 2, right 1, up 2, right 1, up 2, right 1, etc. Or down 2, left 1, down 2, left 1, etc. Down 2, left 1, down 2, left 1. You can keep going like that for a long time. It's a nice dotted line this time, so I connect them with dotted lines. Okay, and I can again make that color a little darker. I keep forgetting on white, you can't see that too well. Here you go. Something like that is going on. Okay, so we notice here we are going to be crossing our parabola in 2 places, aren't we? So we can see that parabola continued up like that. But we're definitely crossing the parabola, the line is crossing the parabola twice. So we will need to find our points of intersection. But first, let's talk shading. Am I shading above the line or below the line? Well, I could pick a test point like 0, 0 that's not on the line itself. Now, I've noticed I've used 0, 0 all day today in this video, but if we had a line or a curve that went through 0, 0, you would have to pick a different point, any point you want, okay? So just make sure you're aware of that. Now, if you plugged in 0, 0 here to your inequality for the line, you'd have 0 is less than 2 times 0, which is 0, plus 4. So is 0 less than 4? Yes. So we would include 0, 0, which is where? Yeah, it's below that line. So we're shading below my line, but we're shading above my parabola. So let's get another color here, like red. Okay, so if I'm shading below my line, but above my parabola, wouldn't that be in this region? So any point in this space. Notice it includes points on the parabola down here, because it was or equal to, but it would not include points on the dotted line, because that was not or equal to. Finally, to get those points of intersection that trap the shaded region, also known as vertices in this case, we would need to solve the system of equations. And so we'd look at our parabola, y equals x squared plus 5x minus 6, and the line, y equals 2x plus 4. And again, substitution is really nice here. If you actually replace this y with what this second y is, you would get 2x plus 4 equals x squared plus 5x minus 6. After solving this quadratic equation, you should end up getting vertices with x values of -5 and 2. So after doing your solving, you're going to have to do that on your own. You'll get x equals -5 and x equals 2. Again, how do you solve that quadratic equation? That's right, you would try to factor, right, or use the quadratic formula. Okay, so now that you know -5 and 2 are the x values, which kind of makes sense on my graph, how would I get the y outputs? Well, I would need to plug those x values into one of my constraints, but which one? Remember in the last case where we had the circle with the parabola, I said plug it into the parabola because it had the lower degree. Similarly, when you have a parabola versus a line, you choose the line because it has the lower degree, meaning it will satisfy them both. Okay, so I'm going to go back to the line, and I'm going to replace x with -5. If I did that, replacing x with -5 here, I would get y equals 2 times -5, which is -10, plus 4. -10 plus 4 is 6. Sorry, -6. And that is where we are down here. We're at -6 for y. On the other hand, replacing x with 2 in that linear equation would give me 2 times 2, which is 4, plus 4, which is 8. So when x is 2, my output is 8. And now I have my vertices which trap my shaded region. All right, so we've done a lot of graphing today and shading and finding points of intersection. It really isn't yours until you've made it yours. So remember, math is not a spectator sport, so go practice. I'll see you next time.